Welcome to this problem-solving session. In this video, we'll tackle the problem titled Count Good Numbers. Together, we'll explore what makes a number good, the constraints of the problem, and the strategies we can use to solve it. Let's dive in and get started. In this problem, we are tasked with identifying and counting a special type of number called a good number. A positive integer qualifies as a good number if, in its decimal representation, the digits at even indices are even, and the digits at odd indices are prime. Here, we use zero-based indexing, which means the first digit is at index 0, the second digit at index 1, and so on. For example, in the number 286, the digits at even indices are 2 and 6, both of which are even. However, the digit at the odd index, 8, is not a prime number. As a result, 286 is not a good number. Given two inputs n, the number of digits in the number, and k, our goal is to count how many n-digit good numbers exist. The result must be returned modulo 10 to the power of 9 plus 7 due to the potential size of the output. The input constraint allows n to be as large as 10 to the power of 15, so we need to focus on creating an efficient solution. Let's look at an example to understand the problem better. If n is 1, the number will have only one digit, and since this digit is at an even index, it must be an even number to qualify as a good number. The possible even digits are 0, 2, 4, 6, and 8, giving us a total of 5 good numbers. The output in this case is therefore 5. Another example is when n equals 4. Here, the digits alternate between even and odd indices. The even indexed positions, 0 and 2, can each take one of 5 possible even digits. Similarly, the odd indexed positions, 1 and 3, can each take one of 4 possible prime digits, which are 2, 3, 5, and 7. Multiplying the number of choices for each index together, we get 5 squared times 4 squared, which equals 400. Hence, the output is 400. For larger inputs, the pattern remains consistent. If n is 50, we have 25 digits at even indices and 25 digits at odd indices. The digits at even indices can each take one of 5 possible even values, and the digits at odd indices can each take one of 4 possible prime values. To calculate the total number of good numbers, we compute 5 raised to the power of 25, multiplied by 4 raised to the power of 25. Since the result can be extremely large, we take the result modulo 10 to the power of 9 plus 7 to ensure feasibility. For this input, the output is 564,908,303. This example highlights the importance of using efficient techniques like modular arithmetic when working with such large computations. The constraints of the problem emphasize the need for an optimized solution. With n ranging from 1 to as large as 10 to the power of 15, it's critical to handle large inputs efficiently. Modular arithmetic and fast exponentiation are key techniques to achieve this. The result must always be returned modulo 10 to the power of 9 plus 7 to handle the immense size of numbers involved. Additionally, edge cases must be carefully considered. For the smallest input, n equals 1, only even digits matter since there is only one position. For the largest input, n equals 10^15, the solution must efficiently compute the result without running into memory or time limitations. It's also important to ensure that the alternation between even and odd indices is handled correctly for both odd and even values of n. These considerations ensure that the solution is robust and scalable. To solve the problem count good numbers, we need to determine all possible good numbers of a given length n. A number is considered good if, for every digit, the digits at even indices are even, such as 0, 2, 4, 6, or 8, and the digits at odd indices are prime, meaning they are one of 2, 3, 5, or 7. However, a challenge arises because the length of the number, n, can be extremely large, up to 10 to the power of 15. This makes it computationally impossible to simply enumerate and check all possible numbers. A brute force approach might involve generating all combinations of digits, where we select from 5 options for even indices and 4 options for odd indices. For a number of length n, the total combinations would be 5 raised to the power of the number of even indices and 4 raised to the power of the number of odd indices. While this gives a conceptual understanding, it quickly becomes clear that this method is infeasible for large n due to the sheer number of possibilities and the exponential growth in computations required. An implementation of the brute force approach could involve using recursion or iteration to generate all possible numbers, ensuring the constraints are met at each step. However, the time complexity for such an approach would be proportional to the total number of combinations, which is approximately 5n/2 4n/2. This grows exponentially with n, making it impractical for large inputs. The space complexity would also grow, requiring n for the recursion stack or for storing intermediate results. To overcome these limitations, we turn to an optimized approach that leverages modular arithmetic. The key observations are that there are always 5 choices for even indices and 4 choices for odd indices, and the sequence alternates between these types of indices. By recognizing this repetitive pattern, we can simplify the computation of the total count of good numbers using the formula 5 raised to the power of ceil, n/2, multiplied by 4 raised to the power of floor, n/2. Instead of directly calculating these large powers, which would be computationally expensive, we use modular exponentiation to compute them efficiently, keeping all calculations within the bounds of a modulo value, such as 10 to the power of 9 plus 7. Using modular exponentiation, the optimized approach ensures that we can compute the required powers in log n time. This is a significant improvement over the exponential time complexity of the brute force method. Additionally, the space complexity of this method is 1, since it does not require any extra storage for intermediate results. The optimized approach is highly efficient and scalable, making it suitable for handling very large values of n. The chosen strategy capitalizes on the alternating structure of the sequence, with even and odd indices repeating in a predictable pattern. By pre-computing powers and applying modular arithmetic, we reduce computational overhead while maintaining precision. Although the optimized approach is more complex to implement, requiring a clear understanding of modular arithmetic, it is both mathematically elegant and computationally robust. Compared to the brute force method, which is easier to code but fails for large inputs due to its inefficiency, this approach represents a trade-off that prioritizes scalability and performance for large-scale problems. In this problem, we need to determine the count of all possible good numbers of a given length n. A number is considered good if it satisfies 2 specific criteria. Digits at even indices, which are 0-based, must be even, meaning they can only be one of 0, 2, 4, 6, 8, while digits at odd indices must be prime, restricted to 2, 3, 5, 7. The challenge lies in the constraints, as n can be as large as 10 to the power of 15, making it impractical to generate and check each possible number. Instead, we need a mathematical approach to efficiently calculate the count. At a high level, this involves modular exponentiation to compute the contributions of even and odd indices separately without explicitly generating numbers. The first step is to understand the choices available for each index. Even indices have 5 options, while odd indices have 4 options. Next, we split the indices based on the length of the number n. For any given n, the even indices are determined by taking the ceiling of n/2, while the odd indices are the floor of n/2. For instance, if n is 7, we have 4 even indices and 3 odd indices. With this division, we can compute the contributions for each type of index. The total choices for the even indices are represented as 5 raised to the power of the number of even indices, and for the odd indices, it is 4 raised to the power of the number of odd indices. To get the total number of good numbers, we simply multiply these 2 contributions together. However, since the value of n can be extremely large, the result may exceed computational limits. To address this, we apply modular arithmetic, specifically modulo 10 to the power of 9 plus 7, to keep the calculations manageable. To handle modular arithmetic efficiently, we compute the contributions for even and odd indices using modular exponentiation. This technique allows us to calculate large powers modulo a given number in logarithmic time. First, we compute 5 raised to the power of the number of even indices, modulo 10 to the power of 9 plus 7. Then, we compute 4 raised to the power of the number of odd indices, modulo the same value. The final result is obtained by multiplying these 2 values, again using modulo 10 to the power of 9 plus 7 to ensure the result remains within bounds. This approach is efficient and avoids the need to explicitly generate or iterate through the numbers. Once these calculations are complete, we can directly return the total count of good numbers, modulo 10 to the power of 9 plus 7. The key insights that make this approach efficient are rooted in modular arithmetic and the properties of the defined constraints. First, modular exponentiation is crucial because it allows us to compute large powers in log, exponent, time, which is much faster than direct computation. Second, the constraints on the digits simplify the problem by reducing the possibilities to only 5 choices for even indices and 4 choices for odd indices. This separation enables us to independently compute the contributions for each type of index. Additionally, because n can be as large as 10 to the power of 15, iterating through all possible numbers would be computationally infeasible. Instead, this mathematical approach ensures scalability regardless of the size of n. Importantly, no explicit storage is required, as the solution relies solely on mathematical computation. The only additional utility needed is a modular exponentiation function, which we will implement in the code. The code implementation begins with defining a constant, mod, which represents the value 10 to the power of 9 plus 7 used for modular arithmetic. We then implement a function for modular exponentiation, which iteratively computes the result of a base raised to an exponent modulo mod. This function is efficient, with a time complexity of log, exponent. Next, the count_good_numbers function calculates the number of good numbers for a given n. It starts by determining the number of even and odd indices based on the ceiling and floor of n/2, respectively. Using the modular exponentiation function, we compute the contribution of even indices as 5 raised to the power of the even count modulo mod, and similarly, the contribution of odd indices as 4 raised to the power of the odd count modulo mod. Finally, these contributions are multiplied together modulo mod to yield the total count of good numbers. This result is then returned to the caller. The algorithm is highly efficient, with a time complexity of log n, due to the modular exponentiation for both even and odd contributions. The space complexity is 1, as the solution does not require additional data structures beyond a few variables. To handle edge cases, consider when n is 1. In this case, there is only one index, and the result is simply the count of even digits, which is 5. For n equal to 2, we have one even index and one odd index, and their contributions are combined accordingly. For extremely large values of n, such as 10 to the power of 15, the use of modular arithmetic ensures that the calculations remain efficient and within computational limits. These edge cases demonstrate the robustness of the approach, ensuring correctness and scalability across all valid inputs. This Python implementation solves LeetCode problem number 1922, count good numbers. The task is to count all possible good numbers of a given length n under modulo 10 to the power of 9 plus 7. A good number has digits at even indices that are even 0, 2, 4, 6, 8, and digits at odd indices that are prime 2, 3, 5, 7. First, we define a helper function, modular_exponentiation, to efficiently calculate base exp %mod using the modular exponentiation technique. This function reduces the time complexity of exponentiation from exp to log exp by repeatedly squaring the base and having the exponent, applying the modulo operation at each step. This is crucial since n can be as large as 10 to the power of 15, making direct computation infeasible. The total number of even index positions is calculated as n plus 1/2, ensuring that the first digit, index 0, is included. Similarly, the number of odd index positions is n/2. Each even index has 5 valid choices, 0, 2, 4, 6, 8, and each odd index has 4 valid choices, 2, 3, 5, 7. Using the modular exponentiation function, we compute the total number of combinations for even index positions, count_even, and odd index positions, count_odd. Finally, we multiply these two values together and return the result modulo 10 to the power of 9 plus 7 to ensure the result fits within the constraints. This implementation is efficient, with a time complexity of log n, and handles the constraints effectively. By computing results for even and odd positions separately, it avoids the need to explicitly generate numbers, making it suitable for very large inputs. Here, we start by defining a constant mod, which is set to 1,000,007. This helps us handle large numbers by ensuring results are taken modulo mod, which prevents overflow. Next, we have a helper method named modular exponentiation. This method efficiently calculates the result of base raised to the power of exp, modulo mod. The approach uses the concept of modular exponentiation by squaring, which reduces the time complexity to O log exp. Within the method, we initialize result to 1. Then, while the exponent is greater than 0, we check if it's odd using exp%2 equals 1. If true, we multiply the current result by the base and take it modulo mod. Regardless of whether the exponent is odd or even, we square the base, apply mod, and have the exponent until it becomes 0. This method is crucial for handling the large powers involved in this problem efficiently. Now, in the count good numbers method, we calculate the number of positions for even and odd indices. Since digits at even indices can take 5 possible values 0, 2, 4, 6, 8, we calculate the number of even positions as n+1/2. Similarly, digits at odd indices have 4 possible values 2, 3, 5, 7, so the number of odd positions is determined as n/2. With these counts, we proceed to compute the total number of valid combinations for even and odd positions. To find the total combinations, we use the modular exponentiation method defined earlier. For even positions, we calculate 5 raised to the power of even positions, modulo mod, and store the result in count even. Similarly, for odd positions, we calculate 4 raised to the power of odd positions, modulo mod, and store it in count odd. Finally, the total number of good numbers is the product of count even and count odd, taken modulo mod to avoid overflow. The result is then cast to an integer and returned. This implementation ensures that we handle the constraints of the problem efficiently, even for very large values of n, by leveraging modular arithmetic and fast exponentiation. In this problem, we need to count all possible good numbers of a given length n. A good number is defined based on its digits positions. Digits at even indices, which are positions 0, 2, 4, and so on, can only be chosen from the set 0, 2, 4, 6, 8, giving us 5 choices per even index. On the other hand, digits at odd indices, like positions 1, 3, 5, and so forth, must be one of 2, 3, 5, 7, leaving 4 choices per odd position. Now, to calculate the total number of good numbers, we first determine how many even index and odd index positions there are in the number. Even indices occur n+1 //2 times, while odd indices appear n //2 times. The total count is the product of 5 raised to the power of the even index count and 4 raised to the power of the odd index count. Since these powers can grow very large, we need to compute them modulo 10 to the power of 9 plus 7 efficiently using modular exponentiation, which is both fast and reliable for handling large numbers in modular arithmetic. Let's look at an example where n is 1. Since the length of the number is 1, there is only one position, which is an even index. Using the formula, the number of even positions is 1 plus 1 //2 equals 1, and the number of odd positions is 1 //2 equals 0. Next, we calculate the contributions from these positions. For the even positions, we compute 5 raised to the power of 1 modulo 10 to the power of 9 plus 7, which gives us 5. For the odd positions, we compute 4 raised to the power of 0 modulo 10 to the power of 9 plus 7, which evaluates to 1 since any number raised to the power of 0 is 1. Finally, we multiply these results to find the total count of good numbers. The result is 5 by 1, %10 to the power of 9 plus 7 equals 5. Therefore, when n is 1, there are 5 good numbers. Now, consider the case where n is 4. A number of length 4 has 2 even index positions and 2 odd index positions. Using the formulas, even underscore positions equals 4 plus 1 //2 equals 2 and odd underscore positions equals 4 //2 equals 2. To compute the contributions, we first calculate 5 raised to the power of 2 modulo 10 to the power of 9 plus 7 for the even positions. The intermediate steps show that 5 squared is 25, and taking modulo 10 to the power of 9 plus 7 doesn't change the result since 25 is less than the modulus. For the odd positions, we calculate 4 raised to the power of 2 modulo 10 to the power of 9 plus 7. Similarly, for squared is 16, and taking modulo 10 to the power of 9 plus 7 again leaves the result as 16. Multiplying these together gives 25 by 16, %10 to the power of 9 plus 7 equals 400. Hence, there are 400 good numbers when n is 4. For a larger example, let's take n as 50. Here, the number has 25 even index positions and 25 odd index positions. Using the formulas, even underscore positions equals 50 plus 1 / 2 equals 25 and odd underscore positions equals 50 / 2 equals 25. The contributions are calculated using modular exponentiation. For the even positions, we compute 5 raised to the power of 25 modulo 10 to the power of 9 plus 7. Modular exponentiation allows us to iteratively reduce the exponent while keeping computations efficient. The final result is 5 caret 25% 10 to the power of 9 plus 7 equals 291172004. Similarly, for the odd positions, we compute 4 raised to the power of 25 modulo 10 to the power of 9 plus 7, which gives 4 caret 25% 10 to the power of 9 plus 7 equals 268435346. Multiplying these results and taking modulo 10 to the power of 9 plus 7, we find 291172004 * 268435346 % 10 to the power of 9 plus 7 equals 7762645154. This means there are 7762645154 good numbers of length 50. The final output for n equals 50 is 7762645154. From this example, we can conclude that modular exponentiation is absolutely essential to handle the large powers that arise in such calculations. Without it, the computations would become infeasible due to the massive size of the numbers involved. The efficiency of modular exponentiation ensures that the solution works in O, log, n, time for both 5 and 4 as bases, making the approach scalable even for very large values of n. This combination of mathematical insights and computational efficiency is what makes the solution both elegant and practical. The time complexity of our solution is primarily driven by the modular exponentiation function. This function, called modular exponentiation, uses the method of repeated squaring to calculate powers under a modulus efficiently. The number of iterations in this function is logarithmic with respect to the exponent, as the exponent is halved in each step. For this problem, the exponents are determined by even underscore positions and odd underscore positions, which are derived directly from the input size n. Specifically, even underscore positions is calculated as n plus 1 / 2, while odd underscore positions is n / 2. Since both are proportional to n, the time complexity of a single call to modular underscore exponentiation is O log n. Now, considering the overall time complexity, there are 2 calls to the modular underscore exponentiation function, one for calculating count underscore even with base 5 raised to the power of even underscore positions, and the other for count underscore odd with base 4 raised to the power of odd underscore positions. Each of these calls independently operates with a complexity of O log n. When combined, the total time complexity is the sum of the two, which simplifies to O log n, since constants are ignored in asymptotic notation. For space complexity, the memory usage depends on the variables and operations within the solution. The algorithm uses a fixed number of auxiliary variables, such as mod, even underscore positions, odd underscore positions, count underscore even, and count underscore odd, all of which consume constant space, or O1. Additionally, the modular underscore exponentiation function is implemented iteratively, so there is no extra space used for recursion. All computations are performed in place, ensuring that the space complexity remains constant. When we consider the overall space usage, we find that the solution does not rely on any additional data structures, and the amount of memory used does not grow with the input size n. Therefore, the space complexity is O1. To better understand the efficiency of this optimized approach, let's compare it to a brute force method. A naive approach would involve generating all possible n-digit combinations and then checking each one to see if it satisfies the criteria for being a good number. For each digit position, there are 5 choices for even indices and 4 for odd indices. This results in a total of 5 caret, even underscore positions, asterisk 4 caret, odd underscore positions, combinations. The time complexity of this brute force approach grows exponentially with n, making it impractical for large inputs. In contrast, the optimized solution avoids this exponential growth by directly computing the result using modular exponentiation. Instead of generating all combinations, it calculates the total count in logarithmic time, reducing the complexity from 5 even underscore positions, asterisk 4 odd underscore positions, to log en. This is a significant improvement in efficiency. On the space complexity side, the brute force approach would require storing all possible combinations, leading to exponential memory usage. The optimized solution, however, performs calculations in place and uses only a constant amount of space, maintaining a space complexity of 1. The logarithmic nature of modular exponentiation is the key to this efficiency. By having the exponent at each step, the number of iterations is proportional to the logarithm of the exponent's value. Since even underscore positions and odd underscore positions are proportional to n, the total time complexity remains log n for the entire computation. Finally, let's analyze the best, average, and worst cases for this algorithm. In all scenarios, the algorithm's behavior depends solely on the size of the input n and not on its specific values. This means that the time complexity remains consistently log n, regardless of the case. Similarly, the space complexity is always 1, since no additional memory is required beyond the constant space used for variables. This consistency in performance makes the algorithm highly predictable and efficient for any input size, demonstrating the robustness of the optimized approach. When approaching this problem, there are a few common mistakes to watch out for. First, miscounting the valid digits for indices is a frequent error. For even indices, there are exactly 5 valid digits, 0, 2, 4, 6, and 8. Similarly, for odd indices, there are 4 valid prime digits, 2, 3, 5, and 7. Misunderstanding this can lead to incorrect calculations of the total possibilities. Another mistake arises when confusing 0-based and 1-based indexing. The rules for even and odd indices depend on the indexing system, and applying the even rule indiscriminately without distinguishing between the two can produce invalid results. Additionally, forgetting to apply modulo operations, specifically modulo 10 to the power of 9 plus 7, at every intermediate step during multiplication can cause overflow errors, especially when working with very large numbers. Finally, attempting a brute force generation of all possible numbers for length n and then filtering for good numbers is highly inefficient. With a complexity of 10 to the power of n, this approach becomes infeasible for even moderately large values of n. Another important point is handling edge cases effectively. For example, when n is 1, special handling is required because there's only one digit to consider. Similarly, for very large values of n, optimized modular arithmetic is essential to keep calculations efficient. Now, let's focus on some insights that are critical for interviews. A key observation here is that the number of valid choices for each digit is completely independent of the others. This independence means we can solve the problem mathematically rather than generating all possibilities. Specifically, even indices always have 5 valid choices, while odd indices always have 4. Using this pattern, we derive the formula to calculate the total number of good numbers, 5 raised to the power of the number of even indices, multiplied by 4 raised to the power of the number of odd indices, and then taken modulo 10 to the power of 9 plus 7. To compute this efficiently, modular exponentiation is a must, reducing the complexity of power calculations to log n. This optimization is particularly important for large values of n. Clear communication is crucial when explaining this problem, especially the distinction between even and odd indices. Emphasizing how modular arithmetic ensures efficiency is also important. For those looking to deepen their understanding, there are several related problems worth exploring. LeetCode 231, Power of 2, involves using modular arithmetic techniques to validate numbers. LeetCode 50, Pow x n, is a great resource for understanding modular exponentiation principles, which are directly applicable here. LeetCode 372, Super Pow, takes modular arithmetic to a more advanced level, making it a valuable exercise for honing these skills. And, of course, revisiting LeetCode 1922, Count Good Numbers, is key for practicing variations of this exact problem and reinforcing the concepts discussed. Finally, let's discuss alternative approaches and the trade-offs involved. The brute force method involves generating all possible numbers of length n and validating them one by one. While simple to understand, this approach is computationally prohibitive with a complexity of 10 to the power of n, making it impractical for large N. A more efficient, but still suboptimal, approach is recursive backtracking. This involves appending valid digits step by step, which reduces the computational load compared to brute force but still incurs significant overhead due to recursion. The optimal approach, however, is mathematical computation. By leveraging modular arithmetic and the properties of exponents, we can directly calculate the result with a time complexity of O log n. This method is not only the most efficient but also aligns with the problem's constraints and is highly scalable. Mastering this technique requires a good understanding of modular exponentiation, but it is well worth the effort for competitive programming and problem solving at scale. Great job! We successfully solved the problem count good numbers and learned about the importance of modular arithmetic and efficient algorithms. Keep practicing similar problems to strengthen your skills, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!